thickness of the parts in a way that it become overly strong, because in that case the ship is going to be heavy, slow and expensive. So basically what we are considering here is optimal design of the structural members of a ship, of the hull of a ship. So the function of a hull. Uh, Actually, the hull can break down from any place, but since the ship is long and slender, so it is there is a high possibility of breaking the ship from the middle. So that is the area where we are focusing. So we are considering the longitudinal strength of the ship's hull. So, in the previous lectures, we discussed various drawings general arrangement lines and midship section. That midship section was actually the middle section, where there is a greater possibility of breakage. So I have a video here. It is an old video in which cargo carrier is container carrier is actually it break down from the middle. Ah,
Hey, would you just click that button?
You cannot have it.
Okay, there is no sound, but you can see the breakage occur at the middle. This is the description. Yeah, there is an animation. Okay. So there was a crack in the lower section, and the water started getting inside, and the ship was broken from the middle. So this is the reason why we are considering the longitudinal strength of the hull, because there is a high possibility of the breakage uh, at that section. So drawing types I have just told you. Function. So the designers usually consider the hull of a ship as a big box with the bottom sides, plates and deck. So safety margin. Since the hull is going to support self weight, weight of the cargo and the forces which it is going to encounter in the ocean. So the third part is not we do not know the third part exactly. So that is the reason we make predictions, and there is less science, less engineering, and more statistics involved, because we do not know how much will be the size of the biggest wave that the hull is going to encounter. So yes. So in the case of the ship, we usually keep the margin between the design limit greater than other components like cars and cell phone, because the uncertainty element is higher in the form of in the case of ship. So this is the weight. This is from this slide is coming from previous lectures. We know the weight is divided into the light weight and dead weight, and on the right side you can see the sum of the two. So what is important is to notice that the distribution of the weight across the length is not same. So due to the uneven distribution, there is going to be greater forces at some section than the other. Weight and buoyancy. We know that the weight is unevenly distributed and it is acting downward, but at the same time, due to the portion of the ship which is underwater, buoyant forces are acting across the length, and they are also not evenly distributed because it depends upon how much portion is inside the water, and they are in the opposite direction. And you can see that since the buoyant forces are coming from the underwater section of the ship's hull, the location is relatively, it is located relatively lower than the weight. Weight is coming from all the containers and other cargo equipment, so that can be higher. So longitudinal loading conditions. Since we are considering the longitudinal strength of the ship's hull, so there are 5 different conditions explained in the book. In the first 3 cases are when the ship is in the still water, there are no waves encountered. In the first case, cargo is evenly distributed, and so is the buoyant forces. In the second case, there is more weight at the ends than in the middle. So there is this condition in which at the bottom side the beam will curve upward. It is called hogging. And in the third case, when there is more cargo in the middle than on the ends, so the beam will curve downwards in the middle, and it is called sagging. In last 2 conditions are when the cargo is uniformly distributed, but the ship is also encountering wave, and the wave in the second last case, it is encountering a wave whose crest is located in the bottom, in the middle of the ship. In that case, the similar situation of hogging, like in the case B, will occur, and in the last, since the wave crests are on the side, on the ends of the ship, so the sagging will happen. But what is important to note is that if the conditions of the load and condition of the ships resulting in the hogging, if they overlap, or the conditions resulting in the sagging they overlap, then it will lead to much worse case, like B plus P and C plus P. So hogging and sagging I have explained, but it is not happening just for one time. Since the ship is traveling through the water and it is continuously encountering waves, so hogging and sagging is happening all the time, and this leads to the fatigue of the structural elements. There is another video. So the camera is showing the whole length of the ship, and you can see the turning like a train. So this is actually the hogging and sagging. It is due to the wave action. Size of vessel. In this slide, there are different dimensions of a ship, and on the bottom side, the ship model is from the Eureka building. Those who visited Eureka building may have noticed this. But the thing is that taking the ratio of length with the breadth and length with the depth can give us the idea about the shape of the ship, because in this case we see the length and depth ratio is greater than 10, so it means that our ship is long and slender. Modes of failure. So in the longitudinal strength case, we 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 consider our whole hull as a simple beam. So the failure of the beam can occur due to the bending and due to the shear. But in the ship case, bending is more critical than the shear. In the first diagram on the right side, you can see there is one point load acting in the middle of the beam that can lead to the failure, and this mode of failure will be due to the excessive bending moment, and the lower fibers of the beam will be subjected to the tension, and on the in the upper fibers there will be compression. And third is just the hand care illustration of how the bending is going to affect. Last two are related with the shear. Second last is normal shear, and the last one is longitudinal shear. These are the different modes of failure. These terms are coming from the strength of materials or mechanics of materials subjects. So you know about stress. It is the reactive force per unit area in response to the externally applied load. Stress can be normal or shear stress depending upon the application of the load. If the load is acting normal to the surface area, it is normal stress. If the load is parallel to the area, it is shear stress. Normal stress can be tensile or compressive, and strain is actually giving us a measure of the deformation. It is a unitless quantity, and it is the ratio of the elongated length or increased length over the original length. It can also be normal and shear depending on the stress. There is a description of normal stress and strain. It is force per unit area, and normal strain is increased length over original length. The relation between the stress and strain is given by the Hooke's law. We know Hooke's law, and the constant is modulus of elasticity, or Young's modulus. Shear stress and shear strain. In case of shear force, we have shear stress. It is usually represented by tau. Previous was sigma, and there is also Hooke's law in shear, and here the constant of proportionality is called modulus of rigidity, and we have Poisson's ratio, which gives us an idea about the ratio between the lateral strain and the axial strain. When we are applying axial load on a simple bar, it is expanding in one direction but contracting in the other. So taking the strains of both and their ratio will give the Poisson's ratio. Elastic and plastic deformation. Elastic deformation is a little in elastic deformation, when we remove the applied load, the body or material is returning to its original shape, while in the case of elastic deformation, this is not the case. There is some strain induced, and it is not returning to its original state. This is the famous stress strain diagram, and the stress strain diagram of any material gives us important mechanical properties about it. And at the start there is before yield strength point there is some proportional limit. In that, up to that point, we have Hooke's law, and the slope of this curve can give us the Young's modulus. above the proportional limit we have elastic limit. So if we will remove the applied load in this range, the material will return to its original form. And then there is yield strength, which marks the boundary between the plastic and elastic region. After that, we see there is a sudden decrease in stress, and then the stress goes on increasing to the ultimate strength. So this point is giving us the ultimate strength of the material which we are testing. And then there is necking, which is a sudden decrease in the cross-sectional area. And then finally there is fracture. So beam and bending, why we are again and again considering the beams, because we are going to consider the entire hull as a beam, and not just hull but component wise. There in the framework there are some structural components which can be further considered as beam. So beam is a structural element whose job is to carry loads. So beam is different from columns in a sense that columns support compressive load. Beam structures in shape. So it's in addition to considering the whole hull as a beam, we can also find the component in the hull of the ship which themselves act as beams. So these are deck beams. Deck beams, we know that we can have multiple decks. So deck beam is basically supporting that deck, and deck is covering over one section, continuous covering. Bulkhead is the separation, like separation wall between different compartments or sections. Then we have frames. They can also be considered as beams. And frames are of two types: transverse frames and longitudinal frames. They are just like the ribs of human body. They support the structure. Airplane also has frames, but they have ring frames. On the right side is the ring block. So how is the hull of the ship is prepared or manufactured? So basically the entire hull is made in different in section wise component, which is called the ring block, and then it is transported to the place where the assembly is made. So this method of making the hull is efficient because it saves time. And one thing to notice is that we have two different bottoms, inner bottom and outer bottom of the hull. This is for the protection and safety purposes. So what is left is stiffeners, girders and webs. So girders are in the longitudinal directions, just like the longitudinal frames, but they are bigger in size than the longitudinal frames. And secondly, there are web frames. They are in the transverse direction, but they are bigger than the transverse frames. I have a video here, so I will try to explain, because there are a lot of parts. Not all can be considered as a beam. Those that can be considered as beam I discussed in the previous two slides. This is just to give you the idea of the arrangement. So the construction is started from the bottom side. In the video, he is calling these greens as solid floor, and then the blue ones are the connections between the inner bottom and the outer bottom, and then there is this brackets, rack brackets. These are the girders, There is one in the middle. There are two types: the middle one and those on the side. The middle one is called the backbone of the ship hull. So these are the transverse frames which I covered in the previous slides. These are the web plates. You see they are in the transverse direction, but they are bigger than the frames inside. And these are the bulkheads, longitudinal and transverse bulkheads. These are the stiffeners, the green ones. They are not visible in the previous drawing. No. Yes, these ones. Now we will just attach the inner plate. And these are the longitudinal frames in the bottom and in the sides. This is the we didn't attach the plate in the bottom side, but there will be a plate, and that will be the inner plate. Okay. So beam loading. This is the since we are considering our hull as a beam, so shear force and bending moment diagrams can provide us with the force and moment at any point. On the left side, there is point load, but on the right side there is uniformly and changing load. But in the case of a ship, the loading will be more complex because of the uneven distribution of cargo and buoyant forces. So in this slide, the function of using brackets is explained. Brackets are small components, but their advantage is that if we use them at the end of the beams, they convert the beam from simply supported beam to fixed beam, and that results in reducing the maximum bending stress to 2/3. So this portion I have included because from the Wikipedia I was learning about how to actually calculate the load. So there are 3 steps. First one is by considering the hull as a simple beam, and that is called the primary hull loads, and load in that case will be the cargo, weight, and wave loads. So first we calculate the load distribution. On the far left side is the weight curve, which is the sum of the light weight and the dead weight. Then since the buoyant forces are acting in the opposite direction, so we combine them and we get the load curve, which is the combination of the weight curve and the buoyancy curve. So we integrate this load distribution curve to get the shear force distribution, and with the help of the shear force distribution we calculate the bending moment curve, and then we can compare the results with the allowable values, and in this way we can estimate. These are the conventional mode of failure. I explained in the start that since the middle part is most vulnerable to the breakage or failure, so hogging and sagging can result in the breakage from this section. And is the neutral axis. So